This video is a little bit of a different video because we are going to change from thinking directly about vectors and matrices and systems of linear equations, and we're instead going to be a lot more theoretical in this video. So instead of thinking about those specific examples, we're going to think about a big picture of what are the mathematical objects that linear algebra deals with. And so to do that, we're going to start by thinking about what a vector can represent. So the easiest way for me to do this is to think about like a vector that I could write as xy. And we're used to thinking about, I could do like a vector 1, 2, or a vector negative 3, 4, or the vector 0, 0. These vectors with two, my examples are going to be vectors with two entries. And we're used to thinking about this in a very different way than how we've thought about it so far in this class. Because in this class, we're seeing this as a set of entries in a column that column forms the vector. We could also do it as a row vector and have it in a row instead. But in math classes prior to this, you have worked with vectors without thinking about it. So if I write the vector 1, 2 as the ordered pair 1, 2, well, what we've done in the past is we've plotted that as a point on the Cartesian plane. So there's another way to think about the vector 1, 2. Instead of thinking about it as a point on the plane or as the point 1, 2 as a point on the plane, we can think of it as the vector that goes from the 0, 0, and points to the point 1, 2. And if we do this, we've got the vector 1, 2. If I multiply that by a constant, say I multiply that by 3, the scalar 3 times the vector 1, 2 gives me the vector 3, 6. And the vector 3, 6 is the vector that points in the same direction but is 3 times longer. And so we can think of a vector as a quantity that has both direction and magnitude or length. So a vector has direction and magnitude. So it's unlike a scalar, which is just magnitude. The vector gives us a direction and magnitude. And we can add vectors together, like vector 1, 2 plus vector, let's say, negative 3, 4. If I look at that, I've got vector 1, 2, which I've already drawn. Vector negative 3, 4 is this vector. And so I can add these vectors together by adding the points to get negative 2, 6, which is this vector. But I can also get to that point by just moving the vector 1, 2 to the end of vector negative 3, 4. Or the vector negative 3, 4, move that vector to the end of vector 1, 2. So I moved that vector up there, and either way, I get to this point. And so I can think of vectors as moving things around. So a vector is like moving things or like finding points on the plane. And so we can think of the plane as a two-dimensional space. We could do a three-dimensional space, and then our vectors would be points with x, y, and z. And they would be defined with three different numbers. So the idea, though, is that let's get away from thinking about it as any specific space. And instead, we're going to define a vector space. So a vector space is a non-empty set. We use the capital letter V to represent the set of all objects that are the vectors. So it's a non-empty set V of objects. What those objects are does not matter. But we will call those objects vectors. On which are defined two operations. The operations are addition and scalar multiplication. So to build a vector space, you have to have a collection of vectors, and you have to define what it means to add those vectors together or to multiply those vectors by a number, by a scalar. And all of the following, for it to be a vector space, all of the following must be true. First, u plus v has to be in our vector space for any vectors u and v. So what this is saying is no matter what two vectors you pick from your vector space, if you add them together, they also have to be that also has to be in the vector space. So you can't have a vector space that when you add vectors together, you get something outside of the vector space. We call this closed under addition. The second thing that has to be true is u plus v. If you add two vectors together, you have to get the same thing if you add them together in the opposite direction. So, so we say that addition is symmetric. The third thing is u plus v plus w has to equal u plus v plus w. So addition is associative. It doesn't matter which addition you do first, you get the same answer. The fourth thing that has to be true is there must be, the vector space V must contain a vector that we call the zero vector such that u plus 0 is equal to u for every vector, for every u in the vector space. So there must be, it must contain an additive 0. The fifth thing that has to be true for it to be a vector space is that for each u in v, for every vector, there is a negative u that's also in v, such that u plus negative u is equal to the 0 vector. So this is the vector space contains an additive inverse. The sixth thing that has to be true is the scalar multiple denoted by c times u must be in V. So if I scale the any vector by any amount, I have to still be in my vector space. So this is closed under scalar multiplication. The seventh fact that has to be true is that c times u plus v has to equal c times u plus c times v. So this is that the distributive property. The eighth one is another distributive property, but this time it's that the scalars c plus d times u is equal to c times u plus d times u. So this is another distributive property. The ninth one is yet another form of a distributive property, and that is that c times du has to equal cd times u. So, sorry, that's really more of an associative property. And the final one is that if I multiply any vector by the scalar 1, I need to get back the same scalar, the same vector. So if you've got a collection of objects, no matter what those objects are, and you define an addition and scalar multiplication on them, and these 10 things are all true, then that is a vector space. This is a really different, really generalized way of thinking about math. So instead of thinking about the details of how vector addition works and things like that, we're just saying, let's assume you can define addition in a way that this works. And what this does is it allows us to think about what different types of things could be vectors. So far, the types of vectors we've looked at are things that could represent like a point in the plane. But there are lots of other different vector spaces. So I'm just going to give one example of that. So for any n greater than or equal to 0, we define the set that we will denote with, sorry, that's the wrong notation, p sub n of polynomials of degree at most n is the set of all polynomials. We can write this set out as the set of all polynomials that look like, I'm going to call it P of t, and we're going to notice I'm calling this a vector because this is going to turn out to be a vector space. The polynomials are vectors of the form some constant plus another constant times, sorry, not x, times t, because I wrote this in terms of t, plus another constant times t squared, etc., until eventually we get to the nth constant times t to the n. And each of the coefficients a0 through an are different constants, different scalars. And t is our variable. So we define p this way. And so we can also define another vector in our vector space, q, as, let's use the letter b. And it does not matter, each of these different b's, b0 is a constant, b1 is a constant, b2 is a constant, each of them are some constant. We can define addition of these vectors this way, p plus q evaluated at t, the addition evaluated at t, is equal to the p evaluated at t plus q evaluated at t. And scalar multiplication can be defined this way. C times p evaluated at t is equal to c times p evaluated at t. It turns out that this forms a vector space. So if we think about adding two vectors together, well, p evaluated at t plus q evaluated at t is just going to be equal to p of t plus q of t by how we defined addition, but that's just equal to a0 plus a1 t plus a2 t squared plus etc. plus an tn, t to the n, plus q evaluated at t is just b0 plus b1t plus b2t squared plus etc. plus bn t to the n. If we rearrange that, we can put a0 and plus b0 together plus a1 times t plus b1 times t gives me a1 plus b1 times t plus a2 plus b2 times t squared plus etc. plus eventually an plus bn times t to the n. But this is just a vector because that meets the definition of the vector space. So we are closed under addition. And I'm not going to go through all of them, but that means that the first category works. And so to show that this is a vector space, I have to do this I have to prove 10 different things. I have to do that kind of a proof for all 10 of these things. I'm not going to go through doing all 10 of those checks. I don't think it is worth our time. However, if you do this, each one of these, they just work. You can try all of these different things and each one will work. So this is a vector space. And that is going to turn out to be very, very important to us later on. But what's really important for us for now is if you have a vector space, so if V is a vector space, V, let's do it, let's just say V with addition and scalar multiplication is a vector space then sometimes you can take part of V and make a smaller vector space. So we will say, so then sometimes part of V can form its own vector space. This leads to a definition. A subspace of a vector space is a set H let me be a little more careful, is a subset that we will call H of V. So it has some, but not necessarily all of the vectors in V, that has these three properties. So if you know you have if you know you're part of a larger vector space, you only have to check three things to know that you've built a subspace. The first one is the zero vector of V is in H. So that zero vector has to be included in H if you've got a subspace, because to be a vector space, you have to have the zero. And so if you're making a subspace, you have to have the zero vector in that subspace. The second piece is that your subspace must be closed under vector addition. And your third thing is that your subspace must be closed under scalar multiplication. So if you add any two vectors in H together, you have to get another vector in H. And if you multiply any vector in H by a constant, you have to get another vector in H. One of the most boring subspaces you can have is the zero subspace. So if I take any vector space V, so if V is a vector space, then I can look at just the set that contains just the zero vector. Is a subspace. It's a really boring subspace, but it is a subspace. So we have this idea of a vector space and a subspace, but let's see how we might actually care about this. So let's consider a vector space. That is, the vector space consists of all vectors of the form x, y, and z with addition and scalar multiplication defined how we've been using them. So defined as normal. Then I can take some number of example vectors. So let's say I take two example vectors. Let's say I take the two example vectors 1, 2, 0, and -1, 0, 1. Now, these two vectors by themselves do not form a vector space because the two vectors don't include the 0 vector, and they aren't closed under addition, because if I add these two vectors together, I don't get one of these two vectors. However, I can talk about the span. So if I say the span of, let's give these names. Let's do it. U equal that, and V is equal to that one. The span of U and V is all linear combinations of U and V. So what do I mean by it's all linear combinations? Well, a linear combination is just some constant times U plus some other constant, not necessarily different, but times V. And if I take all those linear combinations, every way that I can multiply U by some number, 0, -5, 1, 32, pi over 8, whatever, and add it to V multiplied by every possible different number, I will get a collection of vectors. Two of the vectors will be 1, 2, 0. That's the vector I get by taking 1 times U plus 0 times V. Another second vector that is a very clear one is -1, 0, 1. That's when I take 0 times U plus 1 times V. But I could also take, say, 1 times U plus 1 times V. And if I do that, I get 0, 2, 1. So that is a linear combination, so it's in the span of U and V. Or if I take 0 times U plus 0 times V, I get 0, 0, 0. So the 0 vector is in this span. And if I keep doing that for every possible constant C1 and C2, every possible number C1 and C2, I will get infinitely many vectors. That span is going to be a vector space itself. And the reason I know that span is a vector space is if I think about it's a subspace of the vector space produced with x, y, and z with this original vector. So it's a subspace of that because all of the elements here can be written as an x, y, z vector. And so I only have to check 3 things. One of them I already checked. The 0 vector is included. The next one I have to check is that any 2 vectors, say A and B, has to be, if I add those together, they have to be in the span of U and V. But A and B, if they are in the span, well, I know that A has to equal some C1 U plus C2 V, and B has to equal some other values. So let's say K times 1 times U plus K times 2 times V. And A plus B then would be equal to C1 plus K1 times U plus C2 plus K2 times V. But C1 plus K1 is a constant, it's a number, and C2 plus K2 is a number, so A plus B is in my vector space. So the second piece of checking if it's a subspace is true. The third one says any multiple of a vector is in the subspace. So if I have a vector A in the subspace, well, A I know is equal to, since it's in that vector space, I know it's equal to C1U plus C2V for some constant C1 and C2. If I multiply that by C, I get C times A is equal to C times C1U plus C times C2V. But C times C1 is just a number, and C times C2 is just another number. So this is also in that subspace, which means that the span of U and V is, in fact, a subspace of my original vector space. So this is how we can check that something is a subspace. I think that is the biggest ideas I wanted to get across. It is worth noting that not everything is in the subspace. There are vectors that are in that. There are vectors that I can write as 3 different numbers that I can't get to by taking and adding these numbers together, these 2 vectors together. If I tried to find like the vector, say 1, 1, 1, I'm not going to be able to build that vector by taking some constant times u plus another constant times v. That isn't true for any constant. So the number 1, 1, 1 is not in the vector space. So not everything is in this subspace. But the span is a subspace of my original vector space. Okay, I think that's where I'm going to stop on this video. And in the next video, we will talk about linear transformations and column spaces and row spaces of matrices and things along those lines. So with that, I am going to stop here, and we will have another video later on.